Hello everyone, in this video we'll learn about the gravitational force model proposed by Newton. This model says that there's an attractive force between any two masses. So let's consider two masses, m1 and m2, and I'll consider an origin here and draw the position vectors to each mass. So that's r1 to m1, and that's r2 to m2. The choice of the origin will not matter because what really matters is the relative positions of m1 and m2. So this vector here is r2 minus r1. The direction of the force acting on m1 by m2, we're gonna call it f1, points in the direction of r2 minus r1, which is equal to r2 with respect to 1. So according to the model, the force on m1 is F1, which is equal to G m1 m2 over r2 with respect to 1 squared times r2 with respect to 1 over r2 with respect to 1. So this quantity here is the distance between m1 and m2 squared, and this is the unit vector pointing from m1 to m2. What is G? G is the gravitational constant. G equals 6.67408 times 10 to the negative 11 meter cubed per kilogram per second squared is known as the gravitational constant. Let's consider an example. The attraction between Earth and an object of mass m. So I'm gonna draw our very nice Earth with its center here and the object of mass m here. So the Earth has radius r Earth and mass m Earth. We can find these quantities in the table in the back in the appendices of Miriam Craig. I also copied this table and it's on the second page of the preamble of set 11, the set on work and energy. So if I want to look at the force F acting on particle m, force acting on particle m, that would be equal to G, mass of the Earth, m, so that's by the Earth, times the distance between the two squared, which is the radius of the Earth, plus the height between m and the Earth squared, times this vector. Well, this vector, I'm going to call it EZ. So this force is going to point along minus EZ. And guess what happens when you combine these terms if you neglect h? So if h is very much smaller than the radius of the Earth. So for yourself, you're just not too high from the radius of the Earth, very small with respect to the radius of the Earth, then this quantity G me over re squared, this becomes equal to G, 9.81 in SI units, or 32.2 feet per second squared in US units. So that's just the regular equation. F is equal to minus mg EZ, that we know for the gravitational, for the weight force. One more thing, the weight is a conservative force. This is a conservative force. So if I have the force Fg is equal to G MEM RE plus H squared along minus ER, then the potential energy of it is U equals minus G MEM over R. That's it for this video.